So let me start AGEA seminar, the last sessions. The first speaker of today's talk is Ho. He'll talk about revisiting mixed geometry. Okay, then you start.
Okay, thank you very much for the invitation. It's a great pleasure to speak here. So today I will talk about a joint work with Penghui Li on a subject called mixed geometry. So roughly speaking, mixed geometry is a subject that was invented by Bennington, Ginsburg, and Searle in the 90s. And they had motivation from representation theory, but then the subject also had other applications, like in knot invariance. And in fact, it has a lot of applications that I'm not even qualified to talk about. So what I'm going to present today is kind of a slice of the story that inspired me to study this subject from the beginning, at the beginning. So here's kind of the rough outline of the talk today. So I will start with motivation from knot invariance, and then I will move on to tell you how representation theory actually allows us to construct and understand knot invariance. And then I will pose a problem within the framework of representation theory. And then I will say how algebraic geometry actually allows us to solve this problem. And also future work on how to apply this theory and attack various conjectures in the field of knot invariance. Okay, so before I even start with the knot invariance story, let me say right away that mixed geometry is a way to produce a grading on existence category. So suppose someone give you a category, some kind of sheet on some space, and you want to somehow produce kind of the same category, but with some extra grading, so you can extract more information out of it. So that's kind of the general story. So that's kind of the main theme that we're going to see throughout the talk, right? But the motivation at the first step, you won't see grading yet. Okay, so a knot. So because this is an algebraic geometry seminar, so let me start with just a simplest definition of a knot invariant. So a knot or a link is an embedding of a circle or a copy disjoint union of circles into the three-dimensional sphere up to isotropy. So the picture will look like this. So you have a circle, and it can be like linked together in an interesting way, right? And the word isotropy means that you're allowed to move your circle around, but you don't allow different parts of the circle to touch each other. So for example, if you have such an interesting link like so, then you're not allowed to disentangle them. And I was a bit sloppy with the terminology, so in this talk, I will just use the term knot to refer to either a knot or a link. And knot theory in general aims to find invariance, algebraic invariance, so that we can tell different knots apart. We want to find invariants that are hopefully easy to compute and yet powerful, so that we can distinguish many knots. So obviously there are many ways to find such an invariant, but here is one way. So the first observation is that, so it's a theorem, let's say that any link or knot is a closure of a braid. So a braid is something like this. So you have a bunch of strands and some go over or under the other. So it says that whenever you have a knot, you can present it as a braid and then you close it up. So by closure, I mean something like that. Okay, so this is, I start with a 3-strand braid and then I close it up, I get a knot. So in this case, actually just 2 copies of the trivial knot. So it's not that interesting, but you get the idea. And then we construct invariants of braids and show that the invariant under certain Markov moves. So obviously, right, a knot can be represented as a closure of a braid, but there may be multiple ways to represent such a knot. And the second step is to show that it doesn't depend on such a presentation. So what are the Markov moves? So Markov moves, there are two of them. This is the first Markov move, and it's the second Markov move. The first Markov move says that you have two braids, right? And you can concatenate them by put one on top of the other. And because you care about the knot, meaning that you will close your braid afterward. So that means that the order where you concatenate them shouldn't matter in the resulting knot. So that's the box A and B represent different braids, and then you concatenate them. So this property is something called the trace-like property. So it's kind of trace. The trace of AB is then the trace of BA. And the second Markov move, it's about adding an extra strand. If you add an extra strand and you twist this like so, and then you can easily convince yourself that once you close up the braid, then the resulting knot stay the same as the one before you add this extra strand. So Markov says that if you have an invariant of braid that satisfies these two that are invariant, with respect to these two different Markov moves, then you actually get a knot invariant. So that's the basics. Okay, so now we move on to algebraic geometry, representation theory, and see how it actually has anything to do with knot invariance. So invariance of braids can be studied using various versions of the Heck algebras. And in this talk, the Heck algebra that I will talk about is something called the Iwahori Heck algebra. It's also called the finite Heck algebra. So here's the definition. So again, now we are interested in braids. So depending on the number of strands, this number n represents that number of strands. And so for any, so really positive number, for any positive integer, the Heck algebra Hn is an algebra over this ring. And it is a deformation of the group ring of the permutation group of n letters. So what do I mean by this? So essentially it's generated by the same element, meaning these simple permutations, Ti, but instead of Ti squared equal to 1, as in the usual group ring of the permutation group, you actually have this more complicated identity. And when Q is equal to 1, you indeed recover Ti squared is equal to 1. And so that is the sense in which this Heck algebra is a deformation of the usual group ring over this slightly more complicated ring. Okay, so let me let braid n be the braid group on n strands. Okay, so the composition is by concatenating braids, by stacking one on top of the other. Then one can show that there's a homomorphism from braid n to Hn. Okay, given by the following. So the I simple crossing, meaning that you have a bunch of things that don't do anything, but then the I guy will be like this. So this is the I simple crossing. Such a braid will get sent to this element, and then you can, and then I mean you have to use this identity somehow, but then you can check that it's actually a homomorphism. All right. So how does it help us with knot invariant? So Jones and Ognianu constructed a trace function from Hn to this ring of two variables, and they actually satisfy the Markov conditions. And so it gives us a way to define a two variable knot polynomials via Heck algebra. And that the resulting knot invariant is something called the Humfly PT polynomial. So it's one of the most powerful knot invariants before people starting to categorify stuff. Right? So this is kind of the story without categorification. So I won't tell you precisely what this trace function is, but soon I will describe for you its categorification. And it actually has a very nice interpretation. Okay. Okay, so now we want to categorify this picture. So what do we mean by categorification? So categorification is, so again, categorification is not really a prescribed process, but rather a statement of what we desire. So what does it mean? So usually you have some construction that gives you a number. Then the categorification of this process says that instead, we should really try to construct, say, a vector space or chain complexes, something that is higher at a higher categorical level up, and then we can recover the number by taking the dimension or Euler characteristic or something of that shape. Right? And if we already have a vector space, for example, they want to do even higher. We say we want a category whose K group will recover the vector space, so something like that. Right? So we want to categorify the Horn-Fleck PT not invariant. So here's at least the one motivation. It's actually unknown if the Horn-Fleck PT not polynomial can detect a knot. Namely, if you plug in a knot and you compute its Horn-Fleck PT polynomial, and you get something trivial, it isn't, at least it's not known whether the knot that you plugged in actually is a trivial knot. But we can categorify it, and we get something called Horn-Fleck PT homology. Another name for it is the Khovanov-Rosansky triply graded link homology, and it is known to detect the unknown. Okay, so there's the word triply graded. So this is the first instant in the top, or you say some grading up here. So when you remember that the Horn-Fleck PT polynomial is a polynomial in two variables, q and t. So if you want to categorify it, then you need at least something that has two grading, so that when you extract, kind of decategorify, the two gradings become the two variables q and t. And the interesting point is that Horn-Fleck PT homology is actually stronger than just a naive categorification. Actually has three gradings. Okay? So this is actually quite powerful. And so how does one go about categorifying Horn-Fleck PT polynomial? So there are two steps. So the Horn-Fleck PT polynomial started with Heck algebra. So we want to categorify it. So the first step is to categorify Heck algebra, meaning you want to find Hecker categories, namely find the category Hn, whose K group is the, or split K group is the Hecker algebra that we saw earlier. Right? So we but we want to construct a category whose K group recover what we started with. And then we want to categorify the Ognianus trace, Jones Ognianus trace. And then that would allow us to produce Horn-Fleck PT homology. And the resulting thing is triply graded homology theory denoted by HHHL, when you link or not L. So that's just notation. Okay, so so the first step, how do we categorify the Hecker algebra? In other words, how do we construct the Hecker category? So that's a combinatorial way to define the category, the Hecker category via Sergo bimodules. So obviously this is due to Sergo. So in what follows, it will work when it comes to the system, but I will restrict myself to the type AN. So you should think about the group GLN and the group SN, the permutation group, as the Weyl group of the general linear group, and also the root system of GLN. So these are the things that you should keep in mind as we go along in the talk. So here's the definition of the category of Sergo bimodules. So let R be a graded ring that is generated by n variables. So you should think of this Cn as the Cartan of GLN. And is it equipped with the action of the natural action of the Weyl group Sn by permuting the variables. And also this Cn will be placed in graded degree 2. Right? So this is the graded polynomial algebra generated by n elements in graded degree 2. And then the category of Sergo bimodules. So what do we do? So it looks a bit complicated. So let me go through it. So first, you look at the category of graded bimodules over this ring. Okay, and then for its simple reflection Sn, you look at this object. Okay? So this R tensor with R over the SI invariant part of R. So this is still some bimodule. And then you look at the full subcategory in the category of all bimodules of R that is closed under monoidal structure, namely that you have bimodules, so you can tensor them. So you want the full subcategory to be closed under this monoidal structure. And it is additive, means that it has to be closed under taking direct sum. And it has to be idempotent complete, means that it has to be closed under the process of taking direct sum man. Right? So you want the smallest subcategory that is generated by these objects and are closed under these operations. So that's the additive category of circle bimodules. But for the purpose of not, that's not enough. We actually have to also consider the DG category of bounded chain complexes of circle bimodules. So note, here's one thing. So I said the word DG here, but if you don't like DG categories, you can think about it as triangulated categories. There's some technical issue why I have to do DG, but that's a small point, at least for the top. The most important point to keep in mind is that I'm not talking about some derived category of circle bimodule. Namely, my chain complexes are up to homotopy, but I don't invert quasi-isomorphism. So this is an object that you don't usually see in algebraic geometry. Usually you see derived category of some variety or some ring or something, but not just homotopy category of chain complexes of some ring. Right? So this is an interesting point, that one of the reasons why mixed geometry is kind of a subtle subject. Okay, so here's a theorem. There's a split K group of the category of circle bimodule, or the usual K group of the triangulated category of circle bimodule, of chain complexes of circle bimodule, is actually allow you to recover the original Hecker algebra. Okay, so when I say split here, right, it's because I'm taking K group of an additive group, sorry, of an additive category. So there's no short exact sequence to consider. The only operation I have is like taking sum man and taking direct sum. And so I only consider essentially split exact sequence. Would you like to think in those terms? Okay, so which element go to which element? So in the Hecker algebra Hn, right, there are these Ti that generates my object. It actually corresponds to this ring. So this is my module R tensor with R over the SI invariant part of R. So this doesn't look that interesting. The more interesting thing is, how about the I simple crossing, something like this. So here's the construction by Rukia. So Rukia has a construction that associates to this simple crossing, this chain complex. So there's some radial shift and maybe some homological shift, but I ignore them for now. I might have lied a bit, meaning that I might have mixed up TI. Sorry, there are two simple crossing, one on top of the other, one under the other. I think I'm drawing the other one. So one of them is slightly more complicated to write down. This one is just multiplication, but that's a minor point. So the most important thing to remember is that I need chain complexes to talk about elements in the braid group. All right. Yes.
Dư ta có dư ta
Anh đụng tới cái nhãn tưởng hổ gì
đó
đó
có dư đó
nó kìa
Okay. Maybe this should mute. Okay.
hổ gì á.
hổ gì
Okay, so let me.
hổ gì
Màn hình của Quốc Hổ.
Okay, that's my parents. Matt. Okay. Sorry, I didn't know that they were in there. Okay, so all right, so okay, so I just finished the first part where I categorify circle bimodule, categorify Hecker algebra, and I have Hecker categories. Now back to knots. So the next step, I have to somehow categorify the Okhnianu trace construction to actually get a categorification of the Humphrey-Petit polynomial to get the triply graded link homology. So the trace is implemented by Hochschild homology. So it's actually quite nice. So let me go through it. So for any R bimodule M, its Hochschild homology is given by the following formula. So you essentially take the derived tensor of M and R. Right? So R is viewed as a bimodule of R itself, and M is already a bimodule. So you just take this derived tensor. So everything is derived for me automatically, so I won't we usually use the letter L there, but for me, everything is automatically derived. So the word for that is Tor, between M and R. Okay, so let given a braid beta, and let L beta be the closure of the braid beta. Then the Hochschild homology, sorry, the triply graded link homology of L beta is defined as follows. So the first step, by Rookie construction, you get C beta, which is some chain complex of circle by module. Okay, so that's from Rookie. So in particular, I will use the following notation. C beta is a chain complex where the CI, each of the CIs is a circle by module. So Rookie constructed this thing for simple. I only mentioned it for simple crossing, which is tensor them to get all the different braids that you like, because that corresponds to concatenating of braids. And then the next step is also actually very interesting. You take Hochschild homology term-wise, right? So it's important to do this, and obtain a new chain complex. And then you take Hochschild homology, and you take the homology of this chain complex. Okay, so I want to point out that this is also somewhat unusual thing to do, right? You're applying some sort of derived functor, but term-wise on some chain complex that is given to you. This is not something that we usually see in our geometry either. Usually you do some sort of like hypercohomology or hyper derived functor, but this is not it, right? You actually apply this derived functor to this chain complex term-wise. So it's a bit strange. So essentially, there's a spectral sequence that go from this is the page 2. Its homology is the page 2 and converges to the usual hyper thing. But the hyper thing is actually a trivial or not invariant, so it's not that interesting. So now the interesting information lives in page 2. Okay, so now we should get 3 gradings. So let me, because too many gradings floating around, so let me take a step back and remind you where the gradings are. So first of all, each of the CI, right, is a circle by module. And in particular, it's a graded object. So there's one grading for each of the CI. And then there are these I-1, I+1. So we have a complex. So another grading comes from that. And then each homology, we take the Hochschild homology, which is a derived functor. So also has its own homological grading from the functor. So that's another grading. So that's 3 grading in Honflet-PT homology. All right. Okay, so now it's the motivation. The third part of the motivation is to geometrize this construction. So question, how do we geometrize this construction, right? So that's the first step. How do we realize this homotopy carrier of chain complexes of circle by modules as the carrier of some sort of sheaves, either constructible or coherent sheaf on some space or stack that we want to do such a thing. So maybe in 5 minutes, I will explain more why we care about geometrization, but let me actually describe the problem first and then go there. So as I mentioned earlier, right, one of the reasons why it is hard to geometrize is that we have this weird carrier of chain complexes and not the derived carrier of something. And so this is kind of one problem. And second, we have some strange grading. We also need to incorporate it in our study. Okay, so there are previous attempts, obviously. This was actually invented by Bennigsen, Sugar, and Ginsburg. The subject of mixed geometry. So they consider the category of semi-simple complexes of constructible sheaves on G mod B mod B. So when G is GON, the general linear group, then B is the upper triangular, consists of upper triangular matrices. And you look at G mod B mod B. So essentially this G mod B part, right? You can think about it as a flat variety, just the usual flat variety when G is GON. And then when you look at sheaves on G mod B and mod B, then this you can think about it as B equivariant sheaves. on the flag variety. And then they show that this category is equivalent to the category of circle by module, not chain complex anything. And then they just take the category of chain complexes with values in this category. And so just by construction, you force it to be the category of chain complexes of circle by module. So I look a bit artificial, which it is, but after some work, they actually, you can relate it. So it's actually non-trivial, related to the category of constructible sheaves on G mod B mod B itself. So this functor is non-trivial to construct. And this essentially say that the left-hand side is kind of a graded lift of the right-hand side. So that's mixed geometry is about constructing graded lifts. Okay, so that's was done in the 90s. And then a more recent approach, like only 4 years old, is by Sergo himself and Vic and Wendt. So they consider the triangulated category of mixed state motifs on, again, the G mod B mod B. And this category is actually equivalent to the category of chain complexes of Sergo modules right off the bat without doing anything special. So what are the limitations? So the first approach is ad hoc, right? We lose functoriality of sheaves in most cases. So namely, if you just do this construction, given any stack or scheme, you look at pure complexes and look at category of chain complexes in pure objects. Then you don't know how to pull back or push forward along non-smooth morphism or non-proper morphism, right? Because non-smooth morphism, when you pull back, you will lose purity. And for non-proper morphism, when you push forward, you also lose purity. And so you kind of stuck with only very nice morphisms. And also the functor that I said earlier, the functor that goes from the graded version to the category of sheaves, that requires certain semi-simplicity of Frobenius action, which essentially is equivalent to some form of Tate conjecture, which is wide open. Okay, how about the second approach? So the second approach is very sophisticated, and it removes the artificial step of taking the category of chain complexes on something. But there are a couple of caveats. First, it only works with spaces stratified by products of A1 and GN. So it's very special. Oh, I also forgot to say that even though the first approach was ad hoc, it was immensely successful, and it was used by many people, Achar, Bezrukov, Lustig, Rich, Chin, and Yoon, and proved many great theorems. Because luckily, a lot of objects in representation theory do have nice stratifications, and you can kind of leverage that. But it turns out that the objects that we care about that are related to knots don't have these nice stratification. Okay, so back to the second approach by Segovia and Wendt. So they remove this ad hoc step, but it only works for still spaces with a nice product, a nice stratification by these nice spaces, and functoriality of sheaves are only for nice morphisms. So for general space, one of the problems is that if you want a perversity structure, which is very useful in representation theory, it doesn't exist in the general case for the derived category, triangulated category of motives. Essentially, it's conjectural because it depends on the standard conjectures, and that's essentially wide open. All right. So those are the other attempts in the constructible sheaves motives world. How about coherent sheaves? Right. So coherent sheaves we should be slightly luckier because of the grading, right? Grading, for example, the category of graded vector spaces is the same as the category of quasi-coherent sheaves on the classifying stacks of the multiplicative group. Right? So somehow grading is easier to realize, say Q core on BGN in the coherent world compared to the compared to the constructible world. So the story is actually more developed. So this approach in the last 10 years, maybe slightly newer. So Oblomkov and Ozhansky, they use a category of matrix factorizations, and to each beta, they actually realize this triply graded link homology as the cohomology of a certain C stars times C star equivalent coherent sheaf on the Hilbert schema point on C2. In fact, this is conjecture by Gorski, Negus, and Rasmussen. But somehow they circumvent the problem of realizing Hacker category geometrically. So they have a conjecture that actually say how to realize this category in their picture, but it's still conjecture. So again, to be desired, geometric realization of this category. And since this category actually appear in representation theory, actually for now still unclear exactly. I mean, there are obviously expectations, but unclear exactly how their story is related to other part of geometric representation theory that is very relevant to the story, like character sheaves, the stack G mob B, or Bezukov to realization of affine Hacker algebra. So all these things somehow should be in the picture, but somehow still unclear. Okay, so why do we geometrize? Right? Why do people try so hard to geometrize, and what to get out of it? So it's for fun and profit. So obviously I don't need to explain the fun part. So let me explain the profit part. So just generally speaking, once you geometrize something, you can use a lot of powerful methods from algebraic geometry and geometric representation theory to understand the original problem. So more concretely, Gorski and Rasmussen conjecture was about relating Hom-Flippy-T homology and coherent sheaves on Hilbert schema point on C2. And if we find a constructible sheaves, realization of this Hacker category, like the category of chain complexes of circular modules, then we can try to have some sort of, can kind of fit into the general philosophy of geometric Langlands duality that compare constructible and coherent objects. And in general, graded lifts are useful in geometric representation theory. For example, in the story of Koszul duality in the style of Bellingson, Ginsburg, and Sergo. But all the attempts so far have been on a case-by-case basis. And it doesn't, as I said earlier, it doesn't have all the functionality that we like. So it's nice to have a way to construct graded lifts uniformly, essentially for all stacks. And we can use that to actually apply to attack these various problems. Okay, so here's the construction of graded lifts. That is the subject of my work with Peng-Hei Li. So let's start with the general idea. So we start with a naive starting point. So if you construct, if you look at the category of constructible sheaves on G mob B mob B, right, then you run into a problem immediately, namely, there's no grading to speak of. We want to have a graded category. And in fact, when you take the K group of this category, you actually just recover the group ring of W, or Sn in the case of GON. Because this category, this object, right, this stack, right, essentially it's a finite orbit stack by the Brouillard decomposition, where the orbits are given by the Weil group. But this is not what we want, right? We want braids, we want the deformation, we want the Hacker algebra. The group ring of symmetric group is not good enough. Okay, so if you play with analytic sheaves, right, then you know that the story of mixed sheaves. So from the Frobenius weight, so this is part of the story of analytic cohomology that was used by Deligne and then further developed with like Bellingson, Bernstein, Deligne, and Garber. And we want to be able to use Frobenius weights as a grading. Right, so this is the general idea. But we run into a problem immediately. So for the trivial group, right? Just get this category shifts, mixed shifts, constructible mixed shifts on spec FQ. What we really want is the kind of graded vector spaces, so we get this. And the problem is that we have non-trivial extension, joint blocks of Frobenius modules. So given the QL with trivial Frobenius action, there's non-trivial extension between them. And this is not what's happening in category graded vector spaces. So we have to do something smarter. So here's the lesson. The lesson one is that we like weights, but dislike non-semi-simplicity of Frobenius. And as I said earlier, right, this is a serious problem. You see it's up here for a point already. And in general, I mean, there are various parts of Tate conjecture that is related to this. So it's not something that we want to solve, right? I mean, it's not easy to solve Tate conjecture. And here's another interesting part, is there's a decomposition theorem of Bernstein, Deligne-Gaba. Let's say the following. So if you have, actually I forgot to mention the following notation that I've been using on this page. So here, right, I have B1 and G1 and B1. So this one indicates that I'm leaving over spec FQ, so FQ to the 1. And without any subscript, that means that's the same object, but base change to the object closure of FQ. So this thing leaves over FQ bar, whereas this thing leaves over FQ. So that is important for the next observation down here. Let's say is that pure complexes over this quotient stack, but over FQ bar. After you pull back to the algebraic closure, then they become semi-simple. Namely, they split into the direct sum of shifts of intersection complexes that are simple. So they split, there's no extension anymore. But, so if you start with pure, you have to pull back to get this semi-simplicity. Question is, can we be greedy and can we have both? Namely, can we still keep weights, right? But still have semi-simplicity, and that's the question. Right? Because after you pull back, you don't have weight anymore. Before you pull back, you run into this non-trivial extension. So that is the problem we want to solve. Okay, so here's the warm-up of how to attack this problem. So the model is that tensor of categories is like fiber product of stacks. So the reason why this is useful is that there are more categories than just categories of sheaves on some stack. And we will really make use of this model. So again, I introduced the notation slightly late, but let Y1 be an odd stack of FQ. And I denote Yn and Y be their base changes to FQ to the n and FQ bar respectively. Then we can consider the carry of constructible mixed shifts on Yn and the carry of just constructible shifts on Y. But there are more categories in between. So how do we see these categories? So it will make use of this model. So the first thing, so when just in usual algebra, right, to tensor two things, right, there have to be module over something. Then you can use that to tensor relatively over that ring. So one categorical level up. To be able to tensor categories, you have to have some sort of symmetric monoidal category, which plays the role of a commutative algebra object, and you have to have modules over that category so that you can tensor over this symmetric monoidal category. So the one of interest for us is the category of mixed shifts on a point. So point n is spec of FQn. So it's a symmetric monoidal category by just tensoring, usual tensoring. And then you can, for any stacks Yn over spec FQn, you can always pull back something from spec FQn and then tensor with the object inside Yn. So that gives us an action of this category on this category by just pull back and then tensor. So in other words, you can view the carrier of constructible mixed shifts on Yn as a module object over this commutative algebra object that is shift mixed constructible on P on point N. Okay, so warm up. So usually, right, what we do is we look at Yn times over point N point. So this is the algebraic, the base change to algebraic closure. And you note that shifts on a point is literally just vect. So this is what people usually do. But if we take this model to heart, then what we should do to do this relative tensor instead. And one can show that this category actually faithfully embedded into the carrier of shifts on Y. And essentially, the essential image is essentially just all shifts on Y that is a pullback of something from Yn for some N. So it's actually something that is very natural. But this way doesn't give us much, right? Just get a full subcategory, so what? We want a grading, not just a full subcategory of something that we know already. So here's the construction, which is a new shift theory. So here's the definition. So you do the following. So this category, right? Each object there's a notion of weight. So Frobenius act on it with eigenvalues whose absolute values are integral. Sorry, are q to some power that is half integral. And so there's a symmetric monoidal functor from that category to the category of graded vector space by forgetting Frobenius action, but still remember the weight. There's a symmetric monoidal functor from that to that. And so it's natural to just take this tensor product and have a new category of shift because that's the graded shifts on Y. Okay, so for what I wrote down to make sense is that a priori the right-hand side depends on N. But one can prove that in fact the right side does not depend on N. And so we actually get a shift on Y, shift theory on Y itself, and actually does not depend on an FQ form of Y, okay, provided that Y is finite type. And I want to note that all this thing, where such a natural construction, is due to foundational work of Lurie, because I mean, tensor category is something that he did. And relative, I mean, look, the formalism is complicated, but it's very workable. So here's the theorem. The category of graded shifts. So this theory is equipped with a 6-frontal formalism. So you can pull and push and do anything you like. For all morphisms between stacks. It has a perversity structure, right? If you play with motives, then it doesn't exist in general. And moreover, it is compatible with the 6-frontal formalism and the perversity structure on the usual category of mixed shifts and the usual category of shifts over the algebraically closed field. And all these make sense of by using the following functors. So there are natural functors from mixed shifts to graded shifts to usual shifts. So the category is like literally sitting in between, and it's remembering enough of the mixed part of the category of mixed shifts so that you can talk about grading, but it forget enough so that you don't run into this semi-simplicity, non-semi-simplicity of Frobenius. Okay, so
Sorry, can I ask a question?
yes,
So this category is an infinity category or something?
yes, it is infinity category. Yes.
Okay, I see. Okay.
To be able to make sense of this tensor thing, you really need infinity category. But after you construct such a theory and you don't like infinity category, you can take its underlying homotopy category, which is a triangulated category. And if you like triangulated category better, then you could just work at that level. But the construction really needs infinity category to work.
Okay, thanks.
Okay, so question, what about simplicity? So one has to prove it, but it's not hard to prove. And what about this thing that we were after, right? We've been doing all this general thing. And if we plug in G mod B mod B, and it doesn't cover this, then maybe we're doing something wrong. But at least, I want to say that at least there's a good news for the trivial group, just directly from the definition, right? So you're looking at, you replace yn by just point n. So the two things we cancel, I just get that created. So you actually get the correct thing for the trivial group. And look, we still want more, right? We still want some sort of decomposition theorem in the style of Bernstein, Berlin-Garber, without base change to arbitrarily closed field. And we also want this original thing. Right? So those are the things to kind of test that our theory gives the correct answer. Okay, so this actually move on to something called weight structures, which is not well known outside the circle of motive people. So motive people have been studying this for at least 10 years, but outside of that, people haven't really, and some, yeah, Achar and his school also look at weight structure, but outside of that, it's not as well known. So weight structure is like a T structure, but truncations are given in reverse. So that's the first difference. Second difference is that truncation is not functorial. So in T structure, right, truncation is a functor. For weight structure, weight truncation is an existence statement. There's no uniqueness, right? It just exists. So you can think about weight truncation as a way to, if you think about spaces, it's kind of a cellular decomposition of your space. And given a space, there are many ways to realize it as a CW complex, and the cellular decomposition will be different for each of them. Right? So weight truncation has that, the spirit. So here's an example of what a weight. So I won't tell you what I won't bore you with the axioms of weight structure, but let me give you a concrete example of what it looks like. So what, in particular, what do I mean by truncation in reverse? And what do I mean by not functorial? All right. So what do I mean by that? So given A, like the fancy A, given an additive category, and let this A dot be an object in the homotopy category of chain complexes of objects inside A, then I will have the following non-canonical exact triangle. So if I replace W by T, does look, this part, right, does look vaguely similar to T truncation, but the way it's done is very different. So first of all, it's the brutal truncation, right? So usual truncation, T truncation is kind of the smart truncation. And when you remember the definition of smart truncation, you have to use kernel and co-kernel somewhere. And that is something that you can only say in an abelian category. If we are in an additive category, right, you cannot say kernel or co-kernel, so we cannot really use smart truncation. But the brutal or stripper truncation still exists. But here, note the following, right? The less than equal to 0 part actually truncate this part and retain the positive part. So that's what I mean by reverse from the T structure truncation. And then the positive part retains the negative part of the chain complex. So that's what I mean by in reverse. And second, what I mean by non-functorial. So even the zero complex, right, can be realized like is homotopy equivalent to something that looks non-trivial. And so when you are given a non-trivial chain complex that is homotopy equivalent to a zero chain complex, then the weight truncation will be something non-trivial. Right? So in that sense, it's not functorial. You don't just get 0. All right. Okay, so what's so good about weight structure? So let's see the AGEA category or triangulate category with the weight structure. and then its weight hard is an additive category. So that's the first good step. Right? So in usual T structure story, the T hard is an abelian category. Weight hard is only an additive category. And so given an object in a category with a weight structure, you can use the weight truncation to produce a filtration on your object. And then you take associated graded, meaning you take cones. Right? So this is one of the reasons why we have to work in infinity category or DG categories, because cones is not functorial. But that aside, when you take associated graded, meaning taking successive cone, we can produce a chain complex up to homotopy. And so we actually get something called a weight complex functor that goes from your original DG category to the category of chain complexes with value in the weight hard. So at least it gives you a comparison theorem, so a comparison functor from your original category and the category of chain complexes on something. And here's the theorem of Bondarco and Susnilo. So I forgot to say, Bondarco was one of the, I guess, founding fathers of weight structure. So when our home between objects in the weight hard concentrate in convergible degree 0 only, then the weight complex functor is an equivalence of category. So if you start with the DG category whose weight hard satisfies this property, then in fact this functor gives you an equivalence of categories. Right? So really we want to focus on DG categories with interesting weight structure that satisfy this property. Okay, so here's the theorem. So after some hard work, one can show that our category of graded, constructible graded sheaves on Y is equipped with weight structure, and it's actually compatible with the Frobenius weight structure on the category of mixed sheaves on Yn. Namely, remember that there's a functor from here to here, and if you take some mixed complex of weight n, then it does land on the weight n part of the category of graded sheaves, where when I say graded n part is, in this category, it really means I'm using the weight structure in the sense I just talked about. And note that due to non-semi-simplicity of Frobenius, in fact, this category does not have a weight structure. But you really have to do this construction to get a weight structure. And essentially, that's why it is hard to construct graded lifts. So in the literature, people always say, another word for graded lift is mixed version of, right? And when they say mixed version of, it doesn't mean that they just look at the mix complex, but what they really mean is that they need to produce some construction, usually case by case, up until this our result, to produce this mixed version. And then moreover, pure objects in our category is actually semi-simple. So you don't need to base change or anything. So it's kind of a refinement of the decomposition theorem of Benson, Bernstein, Deligne, Garber. So this is kind of the first sign that the category actually are the right thing to consider. And then the second theorem, also drawn with this whole thing is drawn with Peng-Hui Li, is that suppose Yn is just that our home between all the pure objects of weight 0 are pure weight 0. Then our category of graded sheaves is actually nice. Namely, this actually can be realized as the category of chain complexes over its weight hard. And then finally, this condition actually has been checked classically by Sergo for this stack. And so, in fact, he proved this part. I mean, he didn't use graded sheaf, but essentially what he proved can be reformulated as this. And then he also proved something that looks like this. And then that would just automatically give you this equivalence. So this carry actually gives you the right answer, but it works for all stack instead of just this specific case. And it has all the good properties that you would care about when you want to use some shift theory. And I want to have one remark, or maybe two. The first is that I said earlier that forbidden semi-simplicity is some sort of part of the Tate conjecture. So what we did, right, is obviously we didn't say anything about Tate conjecture. We essentially circumvented. We say that for the purpose of representation theory, we do not need Tate conjecture. We just essentially, if you want to produce some graded lift, we just use this category. And that will give us the graded lift with all the good properties that one would care about. So that's the first remark. The second remark is that essentially classically, the only way people produce graded lifts are by this sort of construction, chain complexes on some collection of objects. And so essentially the only graded lifts that people can or people could produce are those that satisfy this nice property, namely our home of pure stuff has to be pure. So those are the only cases when people could actually produce graded lifts. So in case where this thing, right, is not satisfied, this category is still well defined and it's also satisfy all the nice properties of a graded lift, but only now that they become visible after this construction, right? Okay, so why did we go through the whole thing? What was our motivation? So the HHH construction that I mentioned at the beginning actually factors through something called the categorical Hochschild homology, also known as the categorical trace of shift graded on G mod B mod B. So this is circle by module, chain complex of circle by module. Now we have a geometric incarnation. So what is the categorical trace of a DG monoid, the DG category? So it's the same as the Hochschild homology, but we, instead of tensoring algebras, we are tensoring categories, but the definition is the same. You see, then so we see over this thing. There's this ref here instead of op, because for categories, op has another meaning already. So ref, it just means that you just swap the monoidal structure. So here's the theorem in progress. So one of the most basic objects in geometric representation theory is something called character sheaves and something called horocyclic correspondence. They go from G mod B mod B. So here, when I write this fraction notation, that means I'm taking the stack quotient using the adjoint action. So I have this correspondence. And the theorem in progress says that the categorical trace of the category of circle by modules is actually the category of character sheaves, which is a full subcategory of this. Right? So we need to really play with this horocyclic correspondence to be able to prove this thing. And moreover, on G mod B and G mod G, there are no nice stratifications like those who were needed in the usual story of graded lifts. So we had to have some robust enough shift theory to actually push through all of these objects. Okay, so in fact, there's a theorem of Bensby and Nadler that says that essentially the same thing, but without graded. And so they expected there should be a graded lift of their construction, but the theory of graded shift wasn't available back then, so they couldn't even formulate what it should be. And then, almost done. Working directly with, I want to have a remark, working directly with circle by modules, Gorski, Hogan, and Wedrick, they actually also computed, so essentially just algebra, no geometry, computed a categorical trace of the Hacker category. But to make it more explicit, they still had a formality conjecture that they couldn't prove. So there's a work in progress again with Peng Li on resolving this formality conjecture. And in fact, one can relate the category of graded character sheaves and the carry of coherent shifts on Hilbert schema point C2, and that give a way to like a proof for the conjecture by Gorski and Goodson Rasmussen that relates conformity, homology, and Hilbert schema points on C2. And yeah, so thank you very much for listening, and that's the end of the talk.
Okay. Is there any question or comment?
Hello.
Hey, yes.
On page 20, how to see C2, the Hilbert scale of C2 arise naturally. So what's the geometry of C2?
Okay, so very good question. So essentially, so one can prove the following. So again, this is the character sheet. This is work in progress. This is one can actually prove this is equivalent to the category of graded modules over this following ring, C, X, and Y. Semi-direct product with, so I have underlines to X1 to Xn and Y1 to Yn. And when you look at this, right, you see that on Hilbert schema point C2, there's Pochesi bundle whose anamorphism looks the same, and it actually generates the whole category. And so the answer is that you just compute it and you see it. Unfortunately, there's no direct link from this point of view. We expect that there is direct link if you go through the story of a fine hacker category of Bezukavnikov, but that's slightly further out in the future.
Hello.
Yes, does that answer the question?
For other type, the same C2 arise as well.
No. For other type, the category is more complicated. It will decompose into different blocks. It's not C2. I actually don't know the answer for other type. I mean, you can compute what it is, but yeah, I'm not sure whether you can relate it to some Hilbert scheme or not. Is it okay? Does that answer the question?
Okay. Are there any comments? If not, let us thank Tico again.
Thank you very much.
Okay. The second talk will be started at GTM 8:15. Okay. See you later. Okay. Thank you. Thank you, Ho.
Thank you very much.
Okay.